Okay. Thanks, everyone. I'd like to welcome Paul Ross. He did a very interesting series of talks a couple of years ago in Coventry about root cause analysis, and he's here to give us an introduction to it today. So a big hand for Paul.
Thank you, Kirk. Yes, this is about disaster, what happens when disaster, what do you have to do when disaster strikes, and how you go about preventing from happening again. So what qualifies me? Well, I have a rather quirky career. I'm an engineer, but my first professional job was actually as a flying instructor, which is a really cool job, and you get to be involved with accident reports, hopefully just reading them and not contributing to them. Then I worked in oil exploration. Oil industry is quite exciting. When things go wrong, they tend to be quite dramatic, and the final bill tends to have a lot of zeros on the end of it. I worked as a photojournalist for a decade. Then I was an aid worker as an engineer and doing humanitarian work. And I've been a software engineer for quite a long time. I've done Python for about 15 years. I'm afraid that's the only mention of Python in this talk. But along the way through all of that, I've seen quite a lot of accidents and near misses. The accidents have varied from the comic to the tragic, but they've all had a component of human error in them. And this caused me to be very interested in this. I kind of developed sort of professional interest in human error, mainly out of a sense of self-preservation, as I didn't want to be one of the people caught up in some of these accidents. So this talk's in three parts, really. It's about blame, and I hope to convince you that this is not a very good idea for managing disaster. It's about root cause analysis, and I'm going to try and convince you that that's not a good idea for handling disaster or the aftermath of disaster. And then I'll talk about, well, how do you investigate disaster and learn from it? Okay, let's take blame. And if you haven't had any personal involvement in an accident or where are we? Let's take blame first. One of the reasons why blame is not a good response to a disaster is it contains a lot of logical fallacies. Here are some of them. There's a fundamental attribution error. This is where you observe someone in some situation and they behave in a way which you think is bad. You don't realize that they actually have information that you don't have that causes them to do that. And if you had that information, you behave identically to them. It's very easy to look at people who've been involved in a disaster and criticize and blame them along these lines. Another fallacy is an outlier assumption that accidents are quite rare, and when people have made errors that led to accidents, you think these errors are quite rare as well. In fact, human error is incredibly common, and it's very systematic. I always type the word the, T-E-H, backspace, backspace, H-E. It's a systematic error that I'll probably do for the rest of my life. Then there's a fair world hypothesis, another fallacy. This is held by many children and a surprising number of adults as well, which basically says that good things happen to good people and bad things happen to bad people. And then you flip that around, and if you've seen someone in a situation where they've maybe been contributed to an accident, you tend to think that they're bad people and they're worthy of blame. This is a fallacy. There's the illusion of free will. In Western culture, we value free will enormously. It's part of our heritage. Anyone can be president if they want to, is what people say. The trouble is that operators of complex systems are heavily conflicted. They're in charge of production, but they're also in charge of safety, which might run contrary to production. I'm sure software engineers, you know this, because if I say, we need to get this code by Friday, okay, you're having to write code, but you're also having to make sure it's safe code as well. You're heavily conflicted. You don't have free will. Then there's administrative convenience. This is when protecting the system becomes more important than protecting the individual that's been involved in a disaster. This is really common in large bureaucracies like the NHS. It's really common in pretty much any financial organization. So when you see a headline saying it was a rogue trader that caused us all those losses, I'm thinking, yeah, right. Lastly, with blame, if you use blame as a weapon after a disaster, you eliminate a reporting culture. It's been shown in many industries that accidents have always been preceded by incidents that almost came accidents. And if those incidents have been reported, then you could prevent accidents. As soon as you start going around blaming people, then you completely eliminate a reporting culture. We're going to look at that. If you want to create a reporting culture in your organization, and I strongly recommend that you do, you might want to consider this aircraft accident report from 1974. So this is a period where aviation regulators were trying to encourage pilots to report incidents that didn't result in accidents, but something went wrong anyway, so that they could be acted on. And the pilots were understandably concerned, if I report something in great detail, which includes a mistake by me, then what happens to me? What's the comeback on me? So it's a very tense standoff between regulators and pilots trying to develop a way that they could trust each other not to retaliate. And in the middle of that process came this particular accident, which can be summarized pretty much by this one drawing here from the accident report. It's a flight from London, it's a British Airways 747 flight from London to Nairobi. Nairobi Airport is here on the right. It's quite high up, over 5,000 feet. And to the north of it, on the left there, is a very high range of hills. And the kind of drama starts, the top left here, where the aircraft, the radar controller contacts the aircraft and said, you're past the hills, you're cleared to descend to 7,500 feet, which is this red line in the middle here. The first officer reads back the clearance and said, cleared to 5,000 feet. He's misread the clearance, and in fact, 5,000 feet is below ground level here. Now, for some reason, the radar controller doesn't pick up the misread callback and doesn't correct them. So at this time, there's very low cloud, so they're flying an instrument, so cloud's right down on the ground. They come barreling down, straight through their assigned altitude. They're flying quite fast, descending quite steeply. They're trying to catch up time. Cockpit workload is extremely high. They fly straight through their cleared procedure. And what must have been a truly frightening moment, they break through the cloud, and there's the ground coming right at them 200 feet away. They haul up the nose, bang on the power. Takes a while for the aircraft to respond. Comes down to 70 feet above the ground. I guess this ceiling is about 30, 40 feet above, so that gives you how high they were above the ground. The tail was pretty much in the trees. Engines pick up and they climb away to safety. They circle around, land perfectly normally. The captain wants to listen to the tapes, the air traffic control tapes. When he does so, he realizes what I've just told you, that they misread the clearance. He makes a detailed report immediately to London. The whole crew suspended. They're flown back as passengers, and the captain is fired. Now, if you read accident reports, they're written in a very cool, evidence-based language, which comes across as a bit grey and bureaucratic. So this is what this accident report said about the treatment of the crew. I'll let you read it yourself. Not good. This month, okay, 3rd of October, Equifax blames one employee. Imagine if you were this employee or a colleague of this employee and you went to work tomorrow at Equifax and you had to do a tricky deployment to production. You made a couple of mistakes that could be disastrous, but then you catch them in time and everything goes smoothly. You're going to go to your manager and say, look, I made some mistakes, anyone could have made them, we ought to tighten up this procedure. I think you'll just keep quiet, wouldn't you? I would. I think Equifax is doomed to make a load of screw-ups in the future because they got a blame culture created by this management team. They'll probably end up changing their name at some point. Okay, so much for blame. Let's have a look at root cause analysis. What is root cause analysis? It is basically a way of looking at failures where a single failure cascades into a load of other failures. A typical example would be electricity grid going down, something like that. This is commonly used in software engineering, I think wrongly. It's very seductive in software engineering because there's no place to hide, really. If you find a bug in my code, you can go back and look at a commit that I did 2 years ago, and there you go, that's the root cause of this problem. Be careful what you wish for, because I think this is dangerously seductive. I will say there's one good thing about root cause analysis. It's really good at one thing. It's perfect for blame. So I thought for fun we'd do some root cause analysis. I'll give you a disaster that happened, and we'll do some root cause analysis together. So this is from the oil industry. It's quite long ago, so hopefully we can all be forgiven for what happened. It's an X $1 million data error and software error. The X is certainly 10, likely 100, probably 200, 300, who knows, $1 million. It's certainly very large. In the photograph there, you see a truck, which is actually full of very expensive computers and other equipment. And on the back of it, there's a big drum of cable, 10 kilometers of armored electrical cable, which you can connect to these tools in the foreground here and lower them down oil wells and find out all sorts of useful stuff about them. This is what I used to do, by the way, and this is taken in the desert in southern Libya. What you get is, this is what you get from the tools that are lowered down oil wells. This is depth going up the center there, and these are the various sensors and their readings. This log is it's a nuclear log, so the tool is bombarding the formation with high-energy gamma rays and high-energy neutrons and so on like that, and you tell all sorts of amazingly good stuff about what's down there. Really expensive to run one of these things, and really, really valuable, the information it gives. Of course, it's all digitally recorded. There's certain sort of static data associated with this log, and it's usually represented as a header like this, things like the date of the log and that kind of stuff. And I'll draw your attention to two numbers here on the right, which is the latitude and longitude of the well. You might ask, well, how does this information enter the digital record? Because it's not actually measured by an instrument. And the answer is that the engineer would be handed a sheet of paper with a lot of this data on, and you basically transcribe it, you type it in. Now, there actually were two ways of doing that. One is on the command line, you do something like set lati to latitude, set long to the longitude. It's like a key value store, right? And you have to remember the names of all the keys to do this, and there were literally hundreds and hundreds of them. So if you couldn't remember them all, there's another way of doing it. You could run a procedure that would ask you for the information. So you type something like run WSD, I think it was well site data, and it asks you a series of questions, and then you just put the data in. So can anyone see why we might start to be running into trouble here? Yeah, okay. For some reason, this procedure asks the questions in a kind of unusual order, and the engineers put in latitude and longitude and got them flipped around. So it's really common on these logs to see latitude and longitude reversed. I mean, here's one example from the North Sea, and you can see that it's the wrong way around. Okay, so actually none of this matters when you're looking at a single well, because you know where that well is anyway. But in the 1980s, data companies grew up which started to do multi-well analysis. So the idea behind this is very simple, is you find two wells some distance apart, and you look at the logs and you find a similar feature on each one, and that tells you a lot about what's in between the two wells. In fact, you can go further than that. You can actually make complete three-dimensional models of oil fields, or the wells in oil fields, and then you can run simulations like, well, if we drill a well here, can we increase production, and so on and so forth. This is kind of like, so big data's not new, right? This is quite expensive to do in the day, needed a lot of compute power, but it's incredibly lucrative for oil companies, the customers, and the providers of this service. Okay, so welcome to West Africa. X degrees north, X degrees east. This oil field, unfortunately, happened to have the latitude equals longitude line running straight through it, so it wasn't obvious, like our North Sea case, that the latitude and longitude were flipped around. And effectively, you've got this situation where the green dots represent wells that are correctly marked in the correct position. The yellow dots are the assumed position, but the blue dots are the actual position of that well mirrored across this line. Okay, so just to make it clear, this is reality. And this is your three-dimensional computer model. Now, it turns out you don't have to have many wells out of position in this way to make complete garbage of your model, and then complete garbage of the recommendations you give to the client at great expense. So imagine you're the producer of this, and you sell this at great expense to the client. After a year, the client comes back and says, look, our field's actually declining in production. We did all the recommendations that you did. What's gone wrong? You say, well, I've got this technique called root cause analysis. That'll get to the bottom of it. So, sorry, well, I'm gone a bit ahead of myself. Root cause, anyone shout out root cause of this problem? Somebody else's mistake. We'll get to that. Okay, anyone else? That's the one, yes. Okay. Another one, software designer, unintuitive order of questions. I'll put a couple of myself in. People in the know, like myself, that realize this is a problem, failed to prosecute this as an issue. The data processing company didn't do any cross-checking to see if this is right. But this isn't a root cause, is it? I mean, this is just a way of choosing one of these to blame people. We want a root cause, something that joins them all together. Okay? Well, this is what joins them all together. It's actually the client's fault, hiring all these people. So good luck with that. Okay? This is one of the problems with root cause analysis. It doesn't give you an actionable result. Okay? And in fact, I can do all your root cause analysis right here, right now, like this. Okay. The problem actually, part of the problem lies with the word cause. Okay? Because cause is something that you construct after the event. And how you create it depends on what evidence you look for and how you interpret that. And the real problem with root cause is that's really just where you stop looking. So if you tell me what your root cause analysis is, I just know where you stop looking. So think of that Equifax case where it was all down to one employee not patching a system. That's what they think is a root cause. I would say that's where you start looking. Why did he not do that? He or she not do that? What was their training? What was their responsibilities? What are the procedures, etc.? Also, if you're looking at causes, do not confuse causes with conditions. So in 2010, BP had a big blowout in the Gulf of Mexico, which caused the largest environmental disaster in American history. And this is part of the report of that from Congress, the president. And they're basically saying, that the decisions that BP and others made to save time and money were the cause of the accident. And they helpfully give a little table down here of some of these decisions. Well, I've worked as an engineer on oil rigs, and you're always trying to save time and money. In fact, that's the whole job of engineering. Engineers do certain tasks cheaper and faster than non-engineers. This is a necessary condition for this disaster, but it is a latent condition in all oil rigs, and they don't all explode. So this is quite wrong to say that these are causes. They are just conditions. So much for root cause analysis. Let's have a look at investigating disaster and some ways in which we might be able to do better than that. First, let's ask, why do we investigate at all, really? I suggest to try and understand at some objective evidential level what happened so that further accidents, not just similar accidents, because you can always prevent the same accident from happening, but further, broader accidents can be prevented. So if you're going to investigate an accident, a disaster, you're going to come across evidence and you're going to have to reason about it and weigh up which bit of evidence is worth more than the other. And unconsciously or not, you're going to have a model in your head, an accident model in your head. So what is your accident model? I'm going to present three quite different accident models in order of kind of like historical context, really. The first model is a sequence of events model, which is, and the idea is accidents can be prevented by removing one of these events. Second one is an epidemiological model, and I always have trouble with that word, I'm sorry. This emerged in the 1990s in civil aviation, and it basically looks at the system as if it's like a human being or a piece of biology. We'll talk about these in a little bit more detail in a moment. And the last one, which is a bit more modern, is commonly called a systemic model, which tries to understand how people and systems interact. Let's have a look at the sequence of events model. This focuses on like cause and effect, A happened, B happened, and so on like that. Tells a relatively simple story, easy to communicate. This is much loved of the media, by the way, which is why you get TV programs like Countdown to Disaster and so on like that. It's a nice, simple story. The problem is, as far as accident investigation goes, is it only encourages very simple countermeasures, which are usually going to be ineffective. And because real systems are highly complex, they'll easily outrun the kind of recommendations that come from this model. And real systems are not only highly complex, but they're changing as well, and this model is soon left behind. So it doesn't really help in future accidents. The epidemiological model is basically thinks that accidents consist of active errors by operators and pre-existing defects. And I think this probably appeals to a lot of software engineers. If you've written some code that handles strings or ASCII strings and then someone puts in a Unicode string, your program might blow up. That is a combination of an active error, putting in a Unicode string, and a latent defect, which is not being able to handle a Unicode string. This is good because it encourages thinking about defenses and better resilience. It's quite often difficult to make meaningful predictions about the future with this kind of model. One thing this has led to, this is going back to BP's disaster in 2010. This is from their document. They point out that there were 8 barriers to this final disaster. All of the barriers had weaknesses in them, and they're represented by holes in the barriers here. And the accident vector managed to find all the way through the holes, and thus you got a disaster. This model was developed by James Reason. I think it's a very good conceptual way of looking at accidents. It's called the Swiss cheese model for information. The systemic accident model is, it tries to focus on the whole system rather than dividing it into parts. It recognizes that systems are constantly changing. Your code base is changing. The whole world is changing. Crucially, it tries to understand why a particular decision made sense at the time. Not made sense now, but made sense then, and why it was made by those operators. So just a couple more pieces. One about investigating human error. Okay. If you're ever involved in doing this, I'd urge you to remember these things. Firstly, generally, nobody comes to work to do a bad job. This is really, really rare. Most people are trying their hardest and trying their best. Human error is not the cause of failure, it's the effect. Okay, and it should be the starting point of the investigation, looking at you, Equifax, not the conclusion. Human error is inevitable, it's systematic, it's not random. Complex systems always require human contribution, so you're always going to have operators there, and the reason for that is because the human element is the most adaptable. You can automate the hell out of everything, but then it becomes very difficult to use that system for something else, and that's why, although aircraft are highly automated now, they still have pilots, because they're the ones that are the last defense against failure. Oh, sorry. My clicker's being a bit funny. And the last thing about investigating human error is that hindsight bias is the biggest obstacle to investigation. So if you're doing an investigation, write hindsight bias on a post-it note, look at it in the morning before you start work, look at it in the evening before you go home. So how do we make progress on reliability? Your organization is not inherently safe, I'm sorry about that, but people in your organization create safety while balancing the needs for production. If you're a manager, recognize that these trade-offs are being made and make it clear what's legitimate and desirable. As a manager, look for the gaps. Particularly between workers, imagine what you think people are doing and what are actually done. What corners are they cutting? What additions are they making? And look for responsibility authority mismatches, where you give them something responsibility for some particular thing, but you haven't given them the authority to carry out that responsibility. And lastly, this is a never-ending process. Catastrophe is always just around the corner, so never forget to be afraid. Okay, this is me. I'd love to hear from you. This book, I have no beneficial connection with this book. I think it's a really good book by Sidney Dekker. If you're interested in this area, I go and get this book. It's quite short, it's well written, it's a great introduction to human error. And so that's a plug for the book. This is a plug for me. That's my GitHub location. I think there's all sorts of cool projects I've done there, and go and check it out. And if you really like them, then hire me. Okay, that's it. Yeah, sure.
Okay, so we've got a couple of minutes if there's any questions at all. Yes.
Going back to your example from the aircraft industry, what kind of lessons can we learn from their way of reporting, their way of dealing with errors in the software industry?
Okay, I think probably the aircraft industry, commercial aviation is a standout example of improvement of safety. I think from 1956 to the present day, the risk of flying on an aircraft has dropped by a factor of 350. And it's a huge degree of effort that they put in many different disciplines. So some of it translates to the software industry, I'm certain. I pulled out incident reporting as one because I see that a lot in my experience in the software industry. We could do a lot better with that. Automation is another one that's been a big contributor to aviation safety, and probably training is another. Remember that aircraft industry is heavily regulated, and therefore it's quite easy to control how aircraft are built and pilots are trained. The software industry is effectively completely unregulated, and so it's very difficult to make progress in some of those areas.
There was one over here as well. I'll take this one first.
I think it's the same question, but on the other side, which is any advice on how to persuade our managers to read an air accident investigation report and understand it?
So reading a what?
Any advice on how to persuade our managers to read and understand an air investigation report? I think it would be good for them. And can you say a little bit about crew resource management, if you think it relevant?
Yes, okay, so this is actually one of 4 talks. As Kurt pointed out, I did these 2 years ago at PYCON. One of them is particularly about what we can learn from the aviation industry. And it goes into some fairly classic aviation accidents. And you mentioned a thing called crew resource management. If you don't know this, I'll tell you briefly what it is. Back in the 70s, aircraft were becoming safer and safer, but then there's a dreadful series of accidents which really just shouldn't have happened on commercial aircraft, like aircraft running out of fuel and that kind of stuff. And it was realized that, and there was a very famous test that NASA did with a bunch of crews that showed that even these extremely experienced captains were quite error prone, and one of the reasons they were is because they weren't listening to their crew. They were basically playing God, if you like. And so the co-pilot was very aware that things are going wrong, but the captain was ignoring them, and that kind of thing. And so there was a big change called into crew resource management, which led to a big reduction of the aircraft accidents. Sadly, this hasn't been copied in other industries. I have a niece who's a midwife in the NHS, and she shares a similar interest to me to this subject, and she says the crew resource management in an operating theatre is really terrible, and they've got a long way to go before they catch up with the aviation industry. Sorry.
Cool, we'll take one last one.
I'm in here during the break if you want to talk as well.
So this might be an overgeneralization, but I think when people come out of university, they're quite nervous about admitting to mistakes and admitting that they've done something wrong. So how do you go about creating an atmosphere, especially among more junior members of a team, where it's okay to admit mistakes and it's okay to admit to errors so that you can prevent larger disasters in the long run?
I guess in some ways, people probably don't like admitting mistakes for a couple of reasons. One is they feel they might be sanctioned in some sense, and you mentioned junior developers, and I suspect they might believe that they're somehow admitting a lack of knowledge as well, not just a sanction. So I can see that you're absolutely right, and I'm sure when I was younger, I wasn't good at admitting mistakes as well. I think perhaps if you could get some of the older team members to address this specifically and talk about mistakes that they have made, because actually human error is just so natural. It's how we learn, and certainly as a developer, I'm making mistakes all the time. I can't even type the word "the" properly, you know. So if you've got senior developers to talk to them and say, this is how you learn, this will pass, this is a learning process, and we won't take sanction against you, and make that really explicit, I think that may go some way to helping.
Okay, thanks again, Paul.
Thank you.